Welcome to the world of engineering mechanics. Here we'll continue our journey to the advanced levels, starting from the basics. Let's start from the basic summary of the previous lesson, mechanics lesson 1. In that lesson, we had an example that if we have a hook and here two forces that two strings are tied with it, and one string has a tension of 500 newton to the right and the other has 300 newton to the left. How to find their sum? Here, if the forces are in the same direction, their sum is simply their mathematical addition. 300 plus 500 is equal to 800. But if the forces are in the opposite direction, the sum is algebraic addition. 500 minus 300, because both forces are actually opposing each other. They're not reinforcing each other. And then we come to the quantities, physical quantities. They have two main categories. One of them is scalar and the other is vector. We started it with examples like 10 kilogram, like 5 seconds, 30 centigrade, or 200 joule, or 750 kilogram per meter cube. These are all density. These are all scalar quantities. They don't ask for direction. We don't say that 10 kilogram in upward or downward or to the left or to the right. It doesn't make any sense. But as opposed to all these quantities, a force actually it asks for not only magnitude but also direction. That is denoted here by angle. As you can see here, this angle is 30-degree angle in the horizontal direction of the force. This is the line of action of the force, the line along which the force is acting. And this arrowhead, it's pointing to this in this direction. But if we point it in this direction while maintaining everything else like length and direction, so the force will completely change. Force is not the same then. Its effect will be different, completely different. So it's called sense. The direction, the arrowhead, the direction of the arrowhead. That is called sense. And the fourth thing is the line of action. The line of action, for example, here I have a body and I am exerting force on this edge, and another person is exerting the same force in the same direction, in the same sense, but it's applying it on this face of the object. So you can say that this one is pushing the object, while this one is pulling it in the same direction. So this push and pull, they are the physical descriptions of force. But the movement is its resulting movement is in the same direction. So this is very important, that where the force is being applied, that is the point of application and the line of action. And we give here an example that if it is a door and a force is being applied at the edge, another force is applied to the center. So the force that is applied to the center will obviously rotate it, but the force that is being applied at the edge, it can easily rotate it, and this is all what we experience every day. Usually, when we want to rotate object, we maintain a distance from the axis of rotation. This is what we already know, even if we don't know the formula behind it, don't know the concept of moment. We're not going into detail. It's just what force can do for us. We are already doing it. So the whole purpose of my lessons is to make us believe that we already know half mechanics. We are already half masters of mechanics. Even a child knows that how to walk. He's using mechanics. He uses it daily. Crawl, walk, or stand, or sit down, or move his limbs. He knows many things. Just a little concentration and focus can make us able to understand the basic principle behind it. Nothing new in it. No tedious algebraic or mathematical definitions or processes are necessary to understand mechanics. At least to get a good grip over the main principles, you don't need much more tedious stuff. So here, now look, this is a line of action of force. If force is moving, if the force is acting along this line, it can easily rotate this object. But if force is being applied here, so you can see that a part of the force will actually be used to rotate this object. It may be a door, it may be another object. But if I apply the force along that board, along that door, along that rotating object, that passes through the center, it will never rotate it. We already know it. But all my viewers know it already. So what's important? The importance is force having a distance from center of rotation, that is d. So we discussed it in that lesson. You can actually go to that lesson and hear the detail, but here we are only summarizing it. And then this is 5 Newton force. I would describe it graphically by line, the arrowhead at this end. So 1 Newton is equal to 1 centimeter is our scale. So 5 Newton is equal to 5 centimeters. And if we want to multiply it by a scalar, it's 2 times 5, become 10 Newton. And 10 Newton is actually 10 centimeter long line, according to the same scale. Because we cannot change the scale for the same example, for the same problem. We cannot change the scale. But if we multiply it by a negative number, what will change actually? The line of action? No. Magnitude? Yes. Magnitude will change because 2 multiplied by 5 is 10. But another thing will also change, and that is the sense. Now, sense is the opposite direction. If this one is pointing to the right, and then this force is pointing to the left, it's the only difference. When I multiply by a negative number, that's it. We call it scalar multiplication. Call it scalar multiplication. And then here you can see that if I am pulling an object, the 10 Newton force to the right and the 10 Newton force to the left, what will be the net effect on the body? The body will not move. We already know, because we are pulling the body with the same force in the opposite directions. 10 Newton here, 10 Newton there. So this 10 Newton is negative, according to our sign convention. So 10 minus 10 is equal to 0 Newton. The 0 Newton is the effect. It's a net effect. Net force is 0. Therefore, the body will not move. Or we can say that there is no net effect of the force. It's actually the resultant force. Now we are actually discussing the resultant forces. And the second one is we have 400 Newton force in one direction and 300 Newton force in the other direction. What will happen? In this case, without knowing a single principle of mechanics, you can say that 400 Newton force will bend and the body will start moving in that direction. But because 300 Newton force out of the 400 will use to cancel the effect of this 300 Newton force, And the remaining 100 Newton force, that will actually force the body to move in its own direction and towards the right. So that is actually the resultant force. But what happens? So in this case, the resultant is 100 Newton. So mathematically, it's 400 plus minus 300. That is equal to 100 Newton. And that's it. And our last topic was, in the previous lesson, was that what if two forces are acting at a right angle with each other, just like this? So the resultant effect, what will happen? Now try to imagine that if I am pulling it this way and you're pulling it upward, what will happen? The object will actually obey both forces, because both forces are not actually opposing each other completely. No, they are actually contributing to the motion in two different directions. This 300 Newton force in the upward direction, and this 400 Newton force in the right direction. What will be the net effect? The body will move to the right and up, right, up, right, up. It means that body will follow this kind of path. So if I remove these two forces, remove that, and here I just draw a single force. That single force is actually the resultant of these two forces. And now, interestingly, trigonometry has a very close relation with this physical phenomenon. Actually, now we are connecting trigonometry with this physical phenomenon. This is totally physical. You can see it, you can observe it. It's not mathematical, but we actually attach or connect mathematics with it because we are in our life very complex problems sometimes, and to design, to create complicated machines, mechanisms, we need mathematics. It's a constraint. We know mathematics is of huge benefit in the study of mechanics, but it cannot replace imagination and deduction. And you should not tend to replace mathematics with imagination. Whenever a mechanism or an object, the body is moving, or it is under the effect of different forces, try to understand what will happen. Try to illuminate the picture, the overall picture of reality. There is nothing other than reality in mechanics. If mathematical law violates the reality, then we have to, we have to amend it. Mathematics obeys reality. If it doesn't obey it, then the law needs some amendment, correction, modification. Got it? I hope you are. You are getting it. And now, here the resultant force. What were the two components? If I go back, if I recall, the two components were actually at right angle with each other. If I connect them in such that here the tail of the second vector of the second force is exactly lies on the head of the first vector force, then the resultant will be head to head. So I will connect it. I will connect the tail of the first vector with the head of the second vector. So we call this method head to tail rule. Head to tail rule of vector addition. It's a method of vector addition. When the forces are at an angle with each other, they are not along the same line, they are not in the opposite directions, then we choose this head to tail rule. There's no limitation of forces that can be computed and to get the sum this way. But this method becomes impractical when there are a lot of forces. For example, if we have tens of forces, so each force demands for the graphical representation. For example, here, if I write one force here, second one here, third one here, fourth one here, like this. Roll these forces according to a scale. Tedious job, very time taking, demanding. But in the end, you must know that the resultant force, it starts from the tail of the first vector and it ends at the head of the last vector. That is called the resultant force. So it's F1, F2, F3, and so on. The resultant is Fr F1 plus F2 plus F3 and so on. We can sum n forces by this method, but it's not practical. Forces are more. Are 10, 12, more than that. But we must know the basic principle, basic law, how to find the sum of two forces when they are at an angle and the angle is not 90 degrees. One force, for example, here, and the second force is at an angle other than 90 degrees. This is theta. It is F1 and F2. So how to find the sum then? So again, imagine that it's an object. One force is pulling it this way, F1, and the other force is pulling it this way, F2. What will happen? Body will move this way and also this way. So a path that is a combination of both paths is in between these two. It can be like this, Body will move this way, not this way, not this way, not this way. Okay. So here, if I draw a dotted line parallel to this line, just following that head to tail loop, I know that forces are arranged this way. Then the vector starting from the tail of the first vector, first force, and ending at the head of the second force is actually the result. So here, if I draw that one, it will be like this. And if I connect this one, this end with this end, is it not a parallelogram? So the resultant is actually the diagonal, the main diagonal of this parallelogram. So diagonally is actually the result. And physically, what does it mean? Physically, it means that remove these two forces. Apply only this force, Fr. So this Fr has the same effect on the body as a combined effect of these two forces, F1. So components are basically the causes, but the resultant is a combined effect. is a combined effect of these two classes. Now, we can make this parallelogram or a triangle. A triangle too, just like that. F1, F2, the third side of the triangle is, and to know this is the result. Here is an interesting result that if I change the order, I draw this F2 first. And F1, I draw it here. Without changing instruction, I just change the order. The order in which I arrange these forces. And then the resultant will be same. Resultant doesn't change. Means that FR is equal to F1 plus F2. That is equal to F2 plus F. So changing in the order of addition, it does not change the result. And we can extend it to more than two forces. If we are ready for it, we can have an introduction to that here. Look, if I have one force like this, F1, another force like this, F2, this one is a result, F4, and F3 goes this way. So it's F3, it's F2, it's F1. This is the resultant of these two forces, F1 and F2. I call it F4. So FR plus F3, it's a resultant of all three forces. And I call it FR prime. So this FR prime is actually the resultant of, if I write it in the form of an equation, comes F1 plus F2 plus F3. First, I added F1 and F2, and then I added the resultant of F1 and F2, that is FR, into F3 to get F prime. So if I change the order and I add first F2 and F3, okay, F2 and F3. So here is that. It's F2 and F3. The sum of F2 and F3. It starts from the tail of F2. It goes up to the end of F3. So it's F2 plus F3. So I write it here, F2, it's F3. And then I add F1. I mean, this one is F2 plus F3. And if I add F1, this vector, right? What's the result of that? Is the result. Now look, if you see carefully, this is F1, this is F2 plus F3, and the resultant is, it starts from the tail of the first force, and it goes up to the tail of the second force, I mean the resultant of these two forces, I mean this green vector. So I can write it this way, that firstly I added F2 plus F3, added these two forces. Okay. Firstly, I added them, and then I add the result of these two forces into F1. So it's just matter of precedence. I mean, first I added this pair, and its resultant is then added into F1. But the combined effect is the same, FR prime. You can see here, F1, this, F1 plus this is the green vector, this one, that is equal to F1. I hope you got it. Can we move on? Okay, good. Linear vectors. Sometimes two vectors are along the same line. If two vectors are along the same line, vector condition reduces to signed algebra. It's much easier. And we started it in the previous lesson briefly, that if one force is 500 Newton in the x direction, for example, this is the x-axis and y-axis, and one force is along x-axis, that is 500 I cap. I cap is a unit vector. You already know it. I'll not go into detail. And the second vector is to the left. That's minus 200 I cap Newton. So FR is equal to 500 I cap minus 200. That is equal to, because we know that I cap is common. It's a unit vector. And unit vector has only one magnitude. Its magnitude is 1. And instruction along x-axis. So I can draw it outside the bracket like this, because it's scalar multiplication. Scalar is being multiplied by a vector. So if I multiply the difference of 500 and 200 y cap, the result will be the same, 300 y cap. So this is the result. Whoops. Common error is that sometimes students, they subtract the smaller magnitude from the logic, but forgot to state the resultant sense. For example, here if I have 200 force, 200 Newton, I cap minus 500 Newton. So what is the resultant? It's 200 I cap minus 500 I cap. So the students usually make a mistake that they write the difference, but they do not write the sign. And the sign gives us the sense. What is the sense? Here the sense is, according to our convention, the right side is positive and the left side is negative. So the resultant is, in this direction, 300 Newton towards left, not towards right. And here, if we are to subtract, because here we are, you can see that we are adding vectors. What if we are to subtract? two vectors. One vector A and subtracted from second vector B. In case, for example, here I have a vector like this, long vector and a shorter vector, but that is collinear. So both vectors are in the same direction. They are called collinear. Call them linear. So this one is B, and this whole is it's A. This vector is A. So what is the difference? Both vectors start from the same point. So without knowing algebra, you can physically see that here. The second vector, this shorter vector, is actually it ends here. And the remaining length of the first vector, or the larger vector, is the difference. So from here to here, this is the difference of both vectors. Provided both vectors are collinear, they are in the same direction. Then, so here, if I write A minus B, can we write it this way, that A plus minus B? Yes, graphically we can understand it. It's another way of seeing this problem. That if, say, larger vector A and it's negative of B, negative of B will be this one. Same length, same direction, opposite sense. So if I draw it from here, it goes up to here. So now, these are two collinear vectors. They are acting along the same line. And you know that their sum is, it starts from the head of the first vector, from the tail of the first vector, it goes up to the head of the last one. So this is the sum of these two vectors. Trustingly, you can say that they are same. The length is same. Because this one is also the remaining length of the larger vector, and it's also the remaining length of the larger vector. So it's just another way of seeing this. Seeing the same situation. Find the difference of two vectors. Okay? So here we can comfortably write that if we are to add, we are to find the difference of two vectors, we can add one vector into the negative of the other vector. Here what we did, look, A plus negative of the second vector. And remember that B minus A is equal to B plus minus A. And they are not same. They are not same because here, if B is a smaller vector, A is a larger vector, then their difference will be a negative vector. For example, if this one is 10 I cap, and this one is 15 I cap, then their difference is minus 5 I cap. That is negative. And graphically, we can see it. If this is B, and the negative of A, draw it from here, goes this way. It's green vector. So this blue vector is B, and the green vector is A, negative A. So the addition of these two vectors is the remaining length of A. Direction is this. So from here to here. And here you can see that the difference of A and B was in this direction, towards right. And here the difference is in the opposite direction. So we can say that B minus A is not equal to A minus. What if the factors are not collinear? If the factors are not collinear and they are not at right angle, how to find the result? Example, this is the vector A. It's a force. So it's force F1 and the second force is making angle theta. This is the result for how to find it graphically. I mean, graphically or algebraically. So here trigonometry comes from. Although it's not a right triangle, but we have a law. It's called cosine law of cosine. Law, that law says that FR, the length, I'm talking about length. What's the length of this vector? That is equal to F1 square, the length of this vector plus the length of this vector, F2 square plus 2 cos angle between two sides. Doing square on both sides, it becomes F1 square plus F2 square plus 2 1 2 theta. So now it's a matter of only substituting the values. If, for example, here I have 500 Newton, this one is 350 Newton. Simply putting the values here, 1 is equal to 500 plus 350 square plus 2 into 500 into 350 into cos theta, and that will be theta 120 degrees. So you can calculate the value. The value will be in numbers, a specific value, and that is actually the result. Now again, I must stress that The resultant is not another force. No, not at all. It's not another force other than F1 and F2. They don't coexist. No, they don't coexist. Actually, the resultant force is the combined fact of the two forces, F1 and F2. F1 and F2 are the reasons. The resultant force is their combined effect. Is their combined effect. And remember one more thing. Here, as you can see, cos 120 degree, it's negative. Because the value of the angle greater than 90 degree, I mean the cos of any angle greater than 90 degrees is negative. So this whole part, this will be negative. So we are minus it from these two. But if angle is less than 90 degree, this angle theta is less than 90 degree, then this ball will be added into these two squares. Because cos 180 minus theta is equal to minus theta. Okay. So therefore, the angle, included angle, if the included angle is, the included angle of this included angle is less than, then what happens? 180, for example, is 70. So 110 is greater than 90 degrees. This cos is negative. This angle is greater than 90 degrees. Sum will be less than 90 degrees. And its cos will be positive. And what about the direction of the result? How to find the direction of the result? For that, you can find this angle by sine law. Here, for example, this angle with the resultant makes an angle of beta with F1. Then you can easily find it by sine law. Then F2 divided by sine beta, opposite end. F2 divided by the sine of opposite end is equal to FR divided by sine theta. So cross multiply, it becomes FR sine beta is equal to F sine theta. So sine beta is equal to FR over F sine theta. This way, you can find that beta is equal to sine inverse FR F sine F1 sine theta. So you can find it. This formula. Put the values here. Resultant force and F1 and the included angle. You can find this angle beta that the result makes, that the result force makes F. This is how you can find the result force, the direction of the result force. What if we are to do the opposite? That sometimes here is a force, and these are the directions. These are axes, and the axes, unlike the Cartesian coordinate system, they are not in 90-degree relation. To resolve this force into its components, what will we do? For example, this is u axis and this one is v axis. This is force F. Now we are doing the opposite. We are splitting this force, dividing this force into vectors. But again, after we have those two forces from u and v direction, this F will be no more there because this is replaced by those two forces. Actually, it is there, but in the form of those components, in the form of those two components. And it's important. Sometimes we are to resolve a force into two forces. Two different actions to see what is the effect of the main force in two different directions. For example, here is a spring, and a body is connected with this spring here and with this spring here, and we are pulling it in this direction. We are pulling that object in this direction. We want to see that what force is actually compressing or extending, stressing the spring, each of the spring. I mean, the springs, they share the common load. What load do they share? So this load sharing is important in the design of different components, machine components. The same single force, two different components are sharing that force. We have to find how much force each component share. In that case, we need to decompose the force, solve force. Do it this way. Here, as you can see, this one. If I draw a parallel line, if I draw a line from here, parallel to this one, here, parallel, this one. So these two axes intersect here. And if you recall that triangle, law of triangles, some different forces get results. In that law, we had a triangle. Here we know the opposite. We know that result. We have to make the components, and we know that one component, its head is the first component. Its head is at the tail of the second component. So let's say this one is FV because it is in V direction. Call it FV. This one is FU. Force component in this direction, that is FU. So if you recall that law of triangles, the first component starts from here, it comes up to this point. Here is a head, another head. And second component, according to that group, tail loop, that number starts from there. So these are two numbers. And the angle between two axes is given. And if that angle is this angle, for example, is theta, so the same angle is here, theta. This angle will be 180 theta. Because the angle of a line is 180, straight line, 180. The interior angle of this triangle is 180 minus theta. We already know this f. We already know it's given. Its sine's log comes from. We can easily find these two sides because we know this angle. Know this angle. We know this side. This one. We already know. And yes, one more thing. We also know what is the angle between this force and u, because the direction of the resultant force is also given. So if that one is here beta, so now you can see that this is side FV, side is FV, and the opposite angle is beta. So beta, that is equal to this F is also given. The largest side, that is equal to F divided by sine 180 minus theta. You can determine the value of V force along V direction. F over sine 180 minus theta multiplied by sine beta. And the same is true for FU. You can also find that FU. So this is the method by which we can resolve a single force inverse complex just to see what load is being shared by each complex. For example, here is a picture. It's hanging on the wall, and its weight is 100 Newton. And here is a strain in this direction, another strain in this direction. So the tension in this string is T F1, and here in this string is F2. So these are two. If I resolve this force into these two directions, along these two axes, I mean here and here, and this is the force. One component along this, second component along this. So this component. These two components are not they are not an angle between. I mean, they are not a 90-degree angle. So this is only one engineering example of this solution of forces. We'll do more examples in the future. in the next lesson. Thank you for staying with us. Wait for the next lesson. Bye.